So we're going to solve October 2023 of Physics Unit 1. Let's start. So again, this question have like what is sectionized into section A and B. Section A contains the MCQs and section B contains your written answers. I think this question will have like 18 to 19 questions. That is the first 10 questions under the MCQ part, and the rest of the are the theoretical written answers, including maths and detailed answers. So we'll just start from the very start. Question 1. It says that a quantity is either a scalar or a vector. Which row of the table is correct? This is quite easy to understand. We have to choose a row which contains one scalar and one vector. So this is a scalar, this is a vector, so option A is the correct answer. For all the other cases, both are vector or both are scalar or again both are vector, right? So only option A is your correct answer. Which of the following is an SI unit for your momentum? For momentum, the equation was actually mass into velocity, right? Which is kg meters per second. And then again, option A is the correct answer in that case. So which of the following, that was the end for your question 2. So moving to question 3, which of the following could be used to describe the elastic limit of a material? Now remember, elastic limit is up to is the point up to which your force and extension are directly proportional, right? And there's another point after elastic limit, that is limit of proportionality. And limit of proportionality is actually indicating that after this point, beyond this limit of proportionality, the object will start to deform permanently. Now over here, the first one says that the stress above the material will not obey Hooke's law. This one actually indicates that not obeying Hooke's law means that beyond this point the object will deform plastically, which is basically the definition for your limit of proportionality, right? Not for elastic limit. So obviously this is not the correct answer. The stress above which the material will be deformed and when the stress is removed. Sorry, what? The stress above which the material will be deformed when the stress is removed. The stress at which the material undergoes a sudden increase in extension, the stress at which the material breaks. This is talking about the breaking stress, and this is about the stress at which the material undergoes a sudden increase in extension. This is about the region, like the making region of your material. For a very small increase in force, there will be large increase in extension. And for these 4 points, I can see that only B will be the correct answer. It says that the amount of force or stress per unit area above these point will is when the material will be deformed when the stress is removed. Like by deformed, it indicates that the object will undergo plastic deformation, right? Like permanent deformation. So even after beyond this point, you remove the force, the object will not return to its original position. And the stress above which the material will not obey Hooke's law. Right, so I was actually wrong. This first one, the stress above which the material will not obey Hooke's law. Hooke's law was entirely related to forced extension, right? That is not the indications for your limit of proportion, like elastic limit. For elastic limit, you have to consider that up to this point, the object will deform temporarily. Beyond this point, the object will deform permanently, right? So this is actually the correct answer. For limit of proportionality, your answer should be that up to this point, force is proportional to extension, right? So this could be the possible answer for limit of proportionality, and also the definitions for force extension, directly proportional to extension. So the correct answer should be option B. Moving on to the next question, they are asking that a ball falls through the air, like through air from rest. Which of the following shows the graph of displacement against time for the ball? As it is falling through air from rest, it means obviously it's going to start from the origin, right? So this graph is not starting from the origin. So option A will not be your one of the possible correct answers. And again, as it is falling, that means we are going to consider that this is a concept of free fall, right? For concepts of free fall, the object always accelerate at 9.81. That means the velocity is increasing. That means initially the object would be like accelerating at at the same rate, but initially the velocity will be very small because the object started from rest, right? So initially the velocity will be like just 9.81, but as time increases, as the object continues to accelerate at the same rate, its velocity will keep on increasing from 9.81 to 19.6, and then again, you keep on adding 9.81 to that. So this should be your possible answers. Initially, the gradient for displacement time graph, gradient is your velocity. Initially, the gradient is very less. As you can see that from this shape, if you draw a tangent over here, the tangent will be very less steep, but finally the tangent is very steeper, which means that over this entire journey the velocity keep on increasing, right, at a constant rate, because your acceleration was constant. So option C is the correct answer. Other than that, nothing of the three options would be the correct answer. So C is the correct answer. Moving on to question 4. A helicopter moves vertically upward with an increasing speed. Which of the following describes the increase in gravitational potential energy of the helicopter? Okay, now it is like moving. Sorry, the helicopter moves vertically upward with an increasing speed, right? Now, since speed is connected with kinetic energy, and they want you to find out, like not exactly. Let's just read the statements over here. The work done on the helicopter by the force of gravity, the total work done by the helicopter as it moves upwards. This is not the correct answer, because obviously they're saying that the total work done by the helicopter as it moves upwards. They're saying that no other forces is acting on the helicopter, but that's not the case, right? Gravity always acts on on this kind of things. If you're moving away from the earth, then gravity will act as long as you're under the gravitational field strength. So for part A, if you focus, it says that the work done on the helicopter by the force of gravity. This kind of indicates that your force of gravity is the one force that is pushing that helicopter away from the Earth's gravitational field strength, which is again wrong, because the gravity will always try to pull that helicopter towards the Earth's crust, right? It will not push it away. This statement A says that the gravity is actually pushing that helicopter away from the Earth's crust. So obviously this is wrong. This is also wrong. And the work done by the helicopter against the force of gravity. This is correct, because your force of gravity is acting in the downward direction, and the force provided by your helicopter engine is actually making that rocket move away from the gravity, right? So this work done is actually against the force of gravity. Gravity acts in the downward direction. This work done is actually is being done in the upward direction, right? So they're in opposite direction. That's why they're against each other. So in that case, option C is the correct answer. So again, moving on to question 6. An object moves with velocity v. The kinetic energy of the object is doubled. Which of the following is an expression for the new velocity of the object? Okay, so for the previous velocity, or for the previous case, the kinetic energy was equals to half mv square, and now for this situation, since the kinetic energy of the object is doubled, right, so it will be like what, 2 ke, which is like just mv square. Now in this case, if you just like make these two equations equal to each other, in that case it will be like mv square is equals to half mv square, right? Wait, in that case the 2 gets divided, the masses gets cancelled out. No, sorry, I am actually making a mistake over here. Okay, so over here we'll just make one expression with this, that previously when the object's velocity was just v meters per second, we'll write that it's going to be like half mv square is equals to kinetic energy. We just take that 2 from the right hand side to the left, like from the left hand side to the right hand side. Now it looks like mv square is equals to 2ke, right? Now in this situation, when the kinetic energy is doubled, right, we can assume that mv square is equals to 2ke. This is double. That means now you have 4 kinetic energy on the right hand side. So it's 4 kinetic energy. You can write mv square is equals to 4 multiplied with kinetic energy. We can break it down. Half mv square. This masses gets cancelled out. This will be cancelled out, and you will finally left with just, this is by the way new velocity. Okay. So over here we can actually represent it like this. V new is actually 2v square under a root, and finally you can write v new is just root 2 V, which is exactly your option A. Now, if there's any problem understanding this line, we assume to make this that new kinetic energy is equals to old kinetic energy. Sorry, old kinetic energy. For new kinetic energy, it was twice in the old kinetic energy, right? So if your old kinetic energy was like 2 kinetic energy and new kinetic energy was automatically twice Ke, in order to balance that out, we have to multiply 2 Ke with another 2, right? So eventually you get like 4 kinetic energy on the right hand side, and on the left hand side you just get like 2 Ke, right? And then again, if you break down kinetic energy in terms of half mv square to multiply with half mv square, you'll be left out with just v square. Okay, it was quite tricky, I would say. So moving on to question 7. The power station gives an electrical output power of 2.1 gigawatt. The power station transfers thermal energy to the surroundings at a rate of this much. Which of the following gives the efficiency of the power supply? For efficiency, we're obviously going to use the equation of what total energy input over total energy output, right? Sorry, total energy output over total energy input. Now, this was actually the useful energy that the power station provides electrical means this was the useful energy, and this was the waste energy. Now, for total energy input, that is a combination for your useful and waste. So for efficiency, that's going to be like output over total input. For output, you have 2.1 gigawatt, and for input, you have 2.1 plus 3.4. So which is exactly your option A, as you can see, 2.1 over 3.4 plus 2.1. So in that case, option A is the correct answer. I hope it was clear. Moving on to question 8. It states that the student applied a tensile force to a metal wire of length x and diameter d. The length of the wire increased by delta x, and the student applied the same force to the same second wire made by the same material. The length of the second wire increased by delta 2x. Now the extension is twice than the original one. Which row of the table could show the length and diameter of the second wire? Now in this situation, diameter, like not exactly diameter, extension was actually inversely related to length, right? So if extension is inversely related to length, that means if you increase the extension twice, in that case your diameter must so not diameter, your length must decrease by 2, right? So in that case, to make these two even, delta x, for example, you have a constant in between them, is equals to strain multiplied with length, right? So if you increase twice x multiplied with length, right, this 2 will actually go to the right hand side, and it will be like, divided by L. So the L actually becomes half. So you can write that L will become half, half L, right? The L was half. Length will be, no, actually they're not representing the length as L over here. They're representing the length also in terms of extension, right? Yeah, as you can see from this part, they are using the extension also to represent that length. They're not using the length separately over here, because over here, oh no, sorry, I made a mistake. The length is also represented with x, right? The extension was a delta x and the length was L. So we can write L is now 0.5x. So from this statement, we can understand that our answer will be from either part A or B. Now, in order to identify which one will be our final answer, we have to discuss about the relationship about diameter and the relationship for your uh, what is it extension, right? So then again, we'll focus on the equation for your original equation, which is force over area extension over length, right? Force over area, this will be actually, will flip out, and this will be the equation for Young modulus. Now in this case, area is actually 1, like pi is equals to d square by 4, right? So if you're increasing the delta x, your diameter should also increase by twice. But as your diameter is always like not used as a diameter in your case, right? Diameter is always used as d square by 4. So in that case, if you increase x by 2 units, that is related to d square by 4. If you increase this also by 2 units, like they are directly proportional, if you use x is like 2x, it's going to be like 2 d square by 4, which will be eventually like 0.5 d. Right, so that's why you have 0.5 d, not 2d. In that case, we can understand that option A will be the correct answer, not option B. So this was the working. You cannot obviously write this workings because these are like MCQs, right? Over here we can see this is like a vector diagram maths. A box of weight W is suspended in equilibrium from a support by two ropes. The tensions in the two ropes are T1 and T2. Which of the following is a vector expression relating the forces acting on the box? Okay, now over here there are two ropes and this weight acting downward. So I'll just draw lines that are very parallel to this the tensions and everything that is acting over here. Okay, that is one force. Then again over there, that's one force. And in the downward direction, there was another force, right? So what I will do is that I'll make a triangle of these three forces. So this was a downward force. Right, I'll just draw the arrows over here. This was a downward force. This was a force like this. And for this one, okay, sorry, just okay, this is maybe not a diagram accurately to scale. Right, so what I'm trying to actually say is that if you connect all these things together, this actually creates a nice and clean triangle, right? So I'll just draw the T2 over here in this space and connect it like this. So the T2 was actually in this direction. As you can see, this one, if you start from over here, this goes to this point and this point and then again this point. So all these forces, this is weight, this is T2, this is T1. All these forces are actually all traveling in same directions. So all the like over here, the summation of all three forces will be equals to 0. There's no other force which is traveling in opposite directions or any other direction, right? So it's just W. So W plus T1 plus T2 equals to 0. In that case, option D is the correct answer over here. Then again, for question 10, a box is pulled along the ground by a rope inclined at an angle of 40 degrees to the horizontal as shown. The tension in the rope is 30 Newton and the box is pulled 5 meters along the ground. Which of the following is the work done on the box? Okay, now in order to find out the work done, you can obviously for this distance that is being traveled is in the horizontal direction, right? So obviously we have to use the horizontal component, that is going to be 30 cos 40, which is force is 30 cos 40 multiplied with 5. If you calculate it, you get almost, sorry, not sure how much do you get. You get 115, almost 150 joules. So in that case, option B is your correct answer for this. Right, so that is it. We are done with our section A. We'll move on to section B. Now for section B, it says that the photograph shows a rocket. The rocket is launched vertically and the rocket's engine gives a total upward thrust of this much, and calculate the initial acceleration of the rocket where the mass of the rocket is also given. Now over here, obviously gravity is also acting on the rocket, right? So the vertical forces that is acting is not only going to be the upward force of thrust, weight will also act. So if I just draw a free body force diagram, as the rocket is accelerating, that means upthrust or this, yeah, upward thrust is certainly greater than your weight, but still weight has a significant importance. So I'll just draw, this is thrust, this is a small weight, and the object is accelerating in the upward direction. So we'll just use resultant force. I refer resultant force with RF is equals to MA. Resultant force is going to be the upward force, thrust 7.3 multiplied with 10 to the power 7 minus your weight, which is basically 5 into 10 to the power 6 multiplied with 9.81 is equals to 5 into 10 to the power of 6 multiplied with your value for A. right? Now again, if you just make A the subject, that is going to be 7.3 multiplied with 10 power 7 minus 5.10 power 6 multiplied with 9.81, and this entire thing will be divided by 5 into 10 power 6. So if you calculate it, you're supposed to get a value of approximately 4.78 meters per second square. But if you go and round and check all the significant figures of the data that is provided in your question, they are in maximum two significant figures, right? So your answer cannot be more accurate than your data. So you cannot keep your answer to three significant figures or greater than two significant figures, because in that case, the higher the significant figures, the more accurate the answer is actually indicating. So your value for acceleration should be written as 4.8 meter per second square in this given space with its own significant unit. And later on for part B, it says that give one reason why the acceleration will increase as the rocket rises. That's because the basic theory of rocket indicates that the rocket is rising because it's burning fuel, right? If the fuel is being burned, that means the overall mass is decreasing. Then according to your F equals to ma, even if it's like what even if it's providing the same thrust from the engine, the resultant force will be greater because now the value for your weight keep on decreasing because mass decreases this time. So we can write, but as this is just a 1 mark question, you can just write that as fuel is being burned, mass decreases, therefore resultant force increases. So resultant force increases, which causes the object to increase its acceleration. Right, but we'll not write till then because it's just 1 mark. So yeah, this is it, all the explanation for your question 11. We'll move on to question 12. Okay, for this question 12a, it just wants you to find out this principle of conservation of momentum, right? That is the basic definition that total momentum before collision is must be equal to total momentum after collision, provided that no external force acts onto the system. So we can write the total momentum So this is it for your part A. We'll move on to part B. A magnet was attached to each glider. The glider collides and stuck together. Like in this situation, the magnets were attracted to, like attached to these ends of the glider. So the magnets would attract each other, and eventually while the magnets are traveling towards each other, they will also carry the gliders with them. And as the magnets get stuck with each other, so the gliders will also get stuck with each other because of the magnets, right? Now the data logger and the sensor were used to record the velocity of A. The velocity recorded after the collision was half the velocity recorded before the collision. And like after the glider A and glider B got attracted to each other and attached to each other, they would both travel in some direction. Okay. Now they are indicating that before the collision, while the magnet were still active, the attractive forces of the magnet were still acting on those glider. The velocity they had in that situation was twice than compared to the velocity after which they are like after collision when they combined together and then started traveling in the same direction. Now we need to explain why, deduce whether these results show that the law of conservation of linear momentum is being obeyed or not. That is because if before collision the velocity was high, the mass was quite small, right? Because not exactly the mass was small, like the mass is constant before collision because glider A and glider B will still have the same mass, but after collision, the velocity is half because now, um, like if I have to explain this in this way, that before collision, what exactly is occurring is that mass of glider A, V of glider A plus mass of glider B, V of glider B, right? This is now equal to mass of A plus mass of B is just combined with one velocity. Now they're indicating that what exactly happens that before collision, the velocity was very high because the mass was distributed equally, right? But after collision, the mass kind of becomes double the original value. So if the mass becomes double the original value, like the mass becomes double to that what it had in the before collision state. Now the velocity will have to decrease by half. If the velocity decreases by half, everything that kind of was high over here will be balanced out by the small increase in velocity. So that's why yes, and in this situation also it obeys the law of momentum. So no need to represent all these things. You can just explain this in just two marking point. That is initial momentum of A was equal to the final momentum of A plus final momentum of B. Um, Wait, just give me a minute. The teacher demonstrated the principle of conservation of linear momentum with using A and B. A and B were initially stationary, then A was pushed gently towards B as shown, right? So what exactly happened? That only A had a velocity before collision, B did not have any velocity. So we'll just write that initial momentum of A was equal to the final momentum of A and B together or combined because finally or after collision, the mass gets doubled than that of the original value. Because after collision, the momentum, so because after collision the mass is double to that of the original value. Original value, right? Therefore momentum, therefore law is obeyed, right? We can write that therefore law is obeyed. So we'll move on to the second part of B2. Explain why the force of attraction between the two magnets did not affect this demonstration. That's because the force of magnets are actually acting as Newton's third law of pair. In this situation, the gliders are obviously accelerating but in opposite direction. And then again, the magnetic forces are equal in size and opposite in direction, but they are acting on like two different objects, right? So eventually what happens is that the resultant force on the system eventually is zero. For example, if particle A was attracted towards this situation and B was attracted towards the left, right? After collision, A and B combines together and kind of becomes a system, right? One combined particle. So in this case, this F and this F will cancel each other out. So there will be no resultant force acting on the system. So eventually forces are constant and the magnetic forces doesn't have any effect over here. So we'll write the answer that the gliders are accelerating in opposite directions because the magnetic forces are equal in magnitude but opposite in direction. And what else? And according to Newton's third law, the resultant forces on the system is eventually zero, right? So we can write that I think we should mention the third law at the very start, that according to Newton's third law, We can just write N3 according to Newton's third law. The forces, specifically magnetic forces, the magnetic forces are equal in size and opposite in direction. So they cancel each other out. Therefore, resultant force of the system is zero. Right, so this is the final answer for your question 12. I hope it was clear enough for everyone. We'll move on to question 13. Question 13. It says the tennis player can practice using a tennis ball machine. The machine projects tennis balls horizontally from a height of 2.54 meter as shown. As it is being projected horizontally, that means it will not have any vertical component of the initial velocity. It will just have the horizontal component of the vertical of the initial velocity, right? Now show that the time taken for the ball to reach the horizontal so to reach the ground is 0.7 seconds. Now, in this situation, obviously, we do not have any vertical component of the initial velocity, but we still cannot use the horizontal component because for horizontal component, if I just draw this over here, for the horizontal components, the problem that arrives is that we do not have any value for the horizontal distance that is traveled by this object, right? We do not have the value for this. For horizontal component, the velocity is always same. Like object is moving with constant velocity in the horizontal motion, right? So in a horizontal motion, we can only use the equation v is equals to d over t. Now, if time is unknown, distance is unknown, in that case, there's no use of having that whatever the initial component of the horizontal component of the initial velocity was. Also in this case we're not also provided with the initial velocity, so we do not have the actual value of your horizontal component of the initial velocity, so velocity 2, right? So in this case we just have to stick to the vertical motion. In vertical motion, obviously your in this case this one actually will be in the downward direction like this. Right, if this is u, v and u horizontal, we do not have the value for u horizontal, but we already know this will be 0. Now again, this is actually the vertical distance, right? Sorry, SV, this is vertical distance, and A is already known, it's going to be minus 9.81. Oh, sorry, it's just going to be 9.81 because this is a single motion. So we can write S equals to UT plus half AT square, where this thing will entirely be 0 because UV was 0, right? So S was 2.52. So 2.54 multiplied with 0.5, 9.81 multiplied with t square. So t in that case will be 2.54 over 0.5 multiplied with 9.81, entire thing under a root. So if you calculate this, you're supposed to get the value of your time as 0.72 second, which is approximately close to 0.7. And then again it says that the ball lands on the ground at a horizontal distance this much from the machine. Calculate the velocity of the ball as it is projected from the machine. Now this is the range, right? The horizontal distance traveled by the ball is 17.89. This black line is the distance of 17.89. You can use your time, and now you can just use your horizontal motion to find out the velocity with which the object was projected from the machine, because over the time your horizontal velocity remains same. So we can use the horizontal um, motion to find out that velocity, initial velocity, because in horizontal motion object moves with constant velocity. So whatever the velocity with which the object was projected from the machine will be the same at the very end of the journey too. So we're just using horizontal motion, which is basically v is equals to d by t. So in that case, since we're trying to find out v, so we do not need to make any other quantity the subject. It's just going to be 17.89 over 0.72. And finally, you get 24.8 meters per second. Moving on to part B. The initial velocity of the ball as it is projected from the machine can be increased. Explain how increasing the initial velocity would affect the angle at which the ball hits the ground. If you are increasing the initial component of the velocity, initial velocity of the ball, right? In this case, obviously the vertical component will not change, right? It's just going to stay the same because the vertical component would still be zero in that situation, right? Now, if I since we are talking about that angle, right, at the very end what exactly occurs is this one also. At the very end, this was your final velocity, and this was maybe the angle with which the object hits the ground, right? This was maybe maybe that was the angle they're talking about. Now in this case, the angle is actually can be calculated using your using your tan theta v horizontal over v, right? So in this case, if you are increasing the value for your what is it? If you're increasing the value of your initial velocity of the ball is projected from the machine can be increased, right? So if you're increasing the value of your initial velocity, in that case, theta must increase, right? Okay, so I was actually making a mistake. So this is VH and VV, right? If I draw a triangle from these, like broken pieces of arrows, this is how the triangle would look like. So in order to find out this theta, it's a vertical component over the horizontal component. So when you're increasing the initial velocity, that means only the vertical component of your final velocity is going to increase, right? The vertical component, only the horizontal component is going to increase, the vertical component will remain the same. So if this is going to stay constant and if this increases, as horizontal component is inversely proportional to theta, so in that case if this increases, the theta must decrease, right? So for your answer to this part B, I'll just copy this diagram and shift it to that part because it is related to part B only. No need to include the diagrams over here because they never asked for the diagram, right? I was just writing it for the better explanation. So for this part, we should write that increasing the initial velocity would cause the horizontal component of the velocity to increase, but will not affect the vertical component. So increasing VV, so then lastly, you can write that according to VH is inversely proportional to theta, theta would decrease. We'll move on to question 14. It says that a student exercises by lifting weights attached to a machine. The machine has a cable as shown in the photograph. The cable passes through a handle and is connected to a weight. So there is a tension T in the cable. The angle between the two sides of the cable is 60 degrees is shown in the diagram. And it also says that the person keeps the cable stationary by applying a force of F 121 Newton. We need to determine the magnitude of the tension in the cable, and this should be a scaled vector diagram. Now over here, this diagram is not also scaled like a diagram to scale. That means the lengths of these lines are not accurate. And then again, you do not have any other sources to calculate the value for this t. So you are supposed to do cosine rule as a rough and then find out the approximate length of these tensions, and then you can just draw the vector diagram as a final stage. So over here, since the tensions in the two cables are equal, so what you're supposed to do is that obviously draw a parallelogram. As you can see, the two cables are like 60 degrees away from each other. So we'll draw that the vertical force is like this is like the horizontal force, or this one, and there's another force over here, this one, and the angle in between them is 60 degrees, right, as we can see, right, this is the 60 degrees. So then again, as your like the student was actually pulling this object in this downward direction, that means this line should actually be used and be connected to over here, right? So I'll obviously not use it. I'll use my auto correction and draw a perfect line over there. So the arrows over here will be like this is towards the right, this tension is upward, and this is the force of that 121 Newton in the downward direction. And over here, if this angle is 60 degrees, that clearly makes this angle as 120 degrees, which means that if you focus on this triangle inside, obviously the sum of a triangle should be 180. If you have 120 at the very center and the two lengths are going to be same, that means over here at each angle the angles will be like 30 degrees. Now for these 30 degrees angles, you can use cosine rule or sine rule to find the value for your attention, right? Now in this case, you have 121 Newton. You're not obviously going to draw a line of 121 centimeters. We'll obviously do scaling over there. So the scaling will be that I'll be dividing every line with 10. So now I have like 12.1 centimeter. um I'm assuming that I do not know that how much space is actually this much in your copy size, but I'm assuming that it's quite okay to draw 12.1 in this space. So the scaling should be like 120. I'll just write it like this, that 121 Newton will represent 12.1 centimeter. Okay, and now from this 12.1 centimeter, I'll draw the I'll do the rough work for your length of tension that you're supposed to draw over here. So for the length of tension, you can use cosine rule, which is basically sine 120 over 12.1 is equivalent to sine 30 over your length for tension, whatever it is. So you can clearly understand it's going to be sine 30 multiplied with 12.1 over sine 120. So if you calculate it, sine 120, sorry, sine 120 multiplied with 12.1 divided by, sorry, sine 30 was at the top. So you approximately get like 6.9858. So we can just write 7 centimeters, right? So in this case, obviously the working for the sine rule should not be included in your answer because this is like outside your syllabus of A-levels physics. So you're supposed to draw a vector diagram, which I already drew over there, just like that similar drawing. And I'll extend this line and draw 60 in this case. I'll just enlarge it a little bit, and obviously the length should be of exactly equal length that you have used in 121, like 12.1 centimeters, 7 centimeters, all this. Now in this case, you have 7 centimeters over here, 7 centimeters exactly over here, and this angle would be like 120 degrees. You should obviously draw this by measuring the angles also, and this should be like 12.1 centimeters. But on your diagram, you're not obviously going to write these lengths over here. On your diagram, you're just going to write that this represents 121 Newton, this represents like 70 Newton in that case, and this represents 70 Newton in that case. And you have like 30 degrees, 30 degrees, and obviously the arrows. Right, so this is how your diagram is supposed to be, and never include these lengths onto your diagram. Okay, the length should be of this much amount, but you do not add those to the informations of your diagram. So that is it for question 14a. We'll move on to question 14b. Now it says that the cable is attached to a 150 Newton weight. Each time the person pulls the handle, the weight moves up a vertical distance of this much Newton, so this much meter, and the weight returns to its original position when the handle is released. The person exercises by pulling and releasing the handle. They do this 90 times in 120 seconds, and the exercise machine displays the average power of the person is 35 watt. Deduce whether the power displayed by the machine is considered with this data. Like we need to identify that what was the actual power used with this entire working. So in order to find out the power, we have to find out the energy, that is basically force into time, right? Now over here the force is 150 Newton. They have already provided, so we can write energy as force into distance, which is basically the formula for work done, but work done and energy are all equal, are all same. So you can just write 150 over the distance, which is 0.25, and you get an approximate energy of 37.5 joules. To find out the power, you have to obviously multiply it with, so divide it with time, which was 120 seconds. But remember, it was done 90 times, so you have to again multiply 90 with that fraction. So it's going to be power is equals to energy over time multiplied with 90, and you get 37.5 over 120 seconds multiplied with 90, and finally you get 28.1 watt, right? And this is the final amount of your power. As you can see that it is not anywhere close to the data of the the machine that displays a 35 watt, right? So they are not equal, and we can say that the data provided by the machine is certainly not consistent. So we can write that since 28.5 watt is less than 35 watt, so data is inconsistent. So yeah, this is it for question 14. We'll move on to question 15. Okay, so for question 15, it says the photograph shows a ladder and a person can use so a ladder that a person can use to climb into the roof space of a building, and it has this ceiling. This is the side, like this is the entire side view, and this is the opening of the roof space. This is the board. This is the ladder, and then the floor. Okay. So when not in use, a ladder is stored into the roof space, and the opening of the door space is covered by a board. The board is hanged into the ceiling at one end. The ladder is attached to the board by a rail as shown below. A small block prevents the board from rotating to the roof space. Okay, so they have ladder, roof space, rail, block, board, hinge, and ceiling. It's quite necessary over here to remember all these points because it will come handy in the next sections. Um, at first, it's just ask the state what is meant by the center of gravity of an object. We can understand that this is a point through which the weight of an object might appear to act. So I'll just write that definition. Point through which weight may appear to act. Appear to act. Okay. So after this, they have part B, the weight of the board of this rail is just 15 newtons, and the weight acts at a distance of this much from the hinge as shown. Okay, so this is the weight of the board, which is acting 0.45 meter from the hinge. The total length of the ladder is 270, and 0.85 meter to the left is the hinge. This is the distance of the hinge from the left side of corner, and the weight of the ladder itself is 54. Assume that the ladder is uniform. Explain why the board and ladder remain in the position. They're assuming that why this ladder, even though obviously it's kind of open after this board, right? Then why does it stay in this position? Why doesn't the board fall off and this ladder slide down, right? Whenever it's not in use, why does it remain in this position? That's because if I draw the weight over here, we'll assume that weight is acting from the center. So this is the direction of your weight, which is like 54 Newton. And then again, this distance can be calculated because as weight is acting from the center, that means this length is actually half of the total, which was 2.7 over 2, that is 1.35. And this much is basically 1.35 minus this value, right? So it's 1.35 minus 0.85. So you get 0.5 over here. That means the distance from the weight of the ladder to that hinge was 0.5 meter. Now, in this case, you have another force acting. This board also actually provides a downward force over here. Because of this downward force, what exactly happens? If you calculate the clockwise moment, the anti-clockwise moment, you'd see that the clockwise moment was greater. Okay, so in that case, your value for this situation, this ladder might like topple over like this, but it's not occurring. That's because this block over there, this is actually the block. This block over there is providing a force in the downward direction, which kind of acts as the total anti-clockwise forces, and eventually the overall moment got balanced together. The anti-clockwise moment got balanced with your clockwise moment, and that's why everything can remain in equilibrium. But we do not know the value for this force, so we cannot calculate it, but we have to explain it in words. So let's just first calculate clockwise moment and anti-clockwise moment. For clockwise moment, the overall working would be that force into distance, that's 50 with 0.45. And if you calculate it, you get, sorry, this is actually anti-clockwise moment. This 50 Newton, the weight of the board, makes this entire thing move in an anti-clockwise direction. So it's going to be anti-clockwise. If we calculate this, this is 22.5 Newton meter. And then again for clockwise moment, you have 54 multiplied with 0.5, and that is going to be 27 Newton meter, right? So these are the values of your moment. We can clearly say that clockwise moment is certainly greater than your anti-clockwise moment. This is the state where I have to explain that the block also provides a downward force, which kind of adds with your anti-clockwise moment and eventually makes it equal to your clockwise moment, so that they all get balanced out, and eventually your total momentum would be zero, and overall the object will remain at equilibrium. Okay, so I'll write it clockwise moment. We can clearly see the difference between the clockwise and anti-clockwise moment is 27 minus 22.5, which is 4.5 Newton meter, right? So we'll write that also into your statement, that clockwise moment, I'll just write cm. The clockwise moment is 4.5 Newton meter greater than the anti-clockwise moment. Then this has to be balanced by that block. This is balanced by that block, which also exerts a downward force. Exerts a downward force, which causes a moment in the anti-clockwise direction, right? In the AC direction. So balancing out all the, sorry, or we can say that, so clockwise moment becomes equal to anti-clockwise moment. Anti-clockwise moment, yeah. Including those maths and writing the statements is certainly important for this part. So this was it for your part B1. We'll move on to part B2. It says that a downward force is required to rotate the board away from the block. This force is required. So this is applied like 0.8 meters from the hinge. We need to calculate this force. This was actually the force that the block was providing, right? So we can certainly find this out if we can find out the difference between the moment, which we already know it was like 4.5 Newton meter, right? And again, they have also like given you the distance. So as we already have the value for the moment, like the change in moment for this part, but that was 4.5 Newton meter. So we can write that resultant moment was actually 27 minus 22.5, and resultant moment will obviously be calculated using this force and the distance. So it's going to be 4.5 over here. So F will be 4.5 over 0.8, and you get 5.63 Newton. Right, so it's 5.63 Newton over here. Okay, then this is it for the working for your question 15. We'll move on to your question 16. For question 16, it says that a steel object is held by an electromagnet. The magnetic force prevents the steel object falling. Suggest two reasons why, so state two reasons why the weight of the object and the force from the electromagnet are not on Newton third law pair forces. That's because the weight, which they're talking about, the weight of the object and the force from the electromagnet. Um, the weight of the object is certainly acting on the object, and the force from the electromagnet is also acting on that object. But yeah, for Newton's third law pair, the forces must act on two different objects, right? But over here, the weight acts on the object, the electromagnet force also acts on this object. So these two forces are actually acting on the same object. And again, they are not of the same type. Weight is a gravitational force, whereas your electromagnet is a magnetic force, right? So we can just write that they are acting on the same body and they're not of the same type. Okay, they asked for two reasons and we wrote that. So okay, so for 16b, it has this steel cable, this support, and this electromagnet connected with the steel cable, and then this steel object, which is obviously connected to the steel cable because of these forces of attraction, like magnetism, right? Now, for part one, it says that when the object is suspended, the strain in the cable is this much, and we have to calculate the Young modulus. These are the additional data that is provided. Cross-sectional area. For Young modulus, we need obviously force and length, and this is the unstretched length. That means this is original length. And from this part, we have the stiffness. Now, from stiffness and yeah, from stiffness, we can somehow calculate the overall force, but we still have to calculate the extension also, right? So what we're supposed to do is this. We have this unstretched length and this strain. From this two data we can calculate the extension, and then again from that extension and this stiffness we can calculate the force. So we'll start with the extension first, because without extension you cannot find force, and then again without extension and force you cannot find the Young modulus. So we'll start with this, that extension is basically going to be the formula for strain is extension over length. So if you have to focus or make extension the subject, in that case the equation would be strain into length. So strain multiplied with length, sorry, I think I wrote Young modulus over there instead. So strain into length. For strain you got 3 into 10 to the power of negative 4 multiplied with length was 3.8. So if you calculate it, you get approximately 1.14 10 to the power of negative 3. So 1.14 10 to the power of negative 3 meters. Now then again for delta x, if you calculate, you can use the equation of k delta x to find out force, which is basically 2.8 10 to the power of 7 multiplied with your value of your extension, which is 1.14 multiplied with 10 to the power of negative 3. Now again, if you calculate, this is the final value of your force, which is approximately 3.19 into 10 to the power of 4 Newton. Now using all these values, you can find out your Young modulus, which is force over area. Force was 3.19 multiplied with 10 to the power of 4 divided by area was 5.1 10 to the power of negative 4. So 5.1 multiplied with 10 to the power of negative 4. That will be further divided by your strain, right, which is already given to you. 3 multiplied with 10 to the power of negative 4. If you just calculate this fraction, you will end up with a value for your Young modulus, which is almost 2.1 multiplied with 10 to the power of 11 pascals. Okay, so this is it for the end of your question 16b1. We'll move on to 16b2. Now, before we move on to 16b2, over here, let's just understand the question very clearly. It says this force extension graph for the steel cable is shown below, and total weight of electromagnet and steel weight. This is the total weight of the electromagnet and the steel object, and this was the extension. When the electromagnet was switched off, the steel object falls off, obviously, and the student states that the change in elastic strain energy stored in the cable will be transferred to the gravitational potential energy of the electromagnet. And discuss the student's statement. You should add to the force extension graph as part of your discussion. Okay, now before we move on to that part, let's draw a second figure over here. For the second figure, I'll just draw the support steel cable connected with your electromagnet, right? But not with the steel object anymore, because I'm assuming that this figure 2 does not have that electricity supply, so the electromagnet does not have these magnetic properties anymore. Now, in this case, when this steel cable, it's not steel cable, when this electromagnet is not acting as a magnet, right? Obviously, the weight or the steel object will not be connected to it. If I have to, for this figure 1, write the downward forces, this is going to be the weight of the electromagnet and also the weight of your steel object, right? So you can write weight of electromagnet plus weight of object. But on the figure 2, obviously the weight of the object is not there. The downward force have certainly decreased, but it still have this weight of the electromagnet, right? So if for this is figure 1, you are supposed to get a larger extension because obviously the forces were quite big. And for figure 2, you are now supposed to get a smaller extension because now the steel object is not connected, right? So you're supposed to get a smaller extension. And this smaller extension is actually considered as the change in height for your gravitational forces of the elastic strain energy. Now, in this case also, even when this object was not connected with your electromagnet, this change in extension was also causing this steel cable to go under elastic strain energy, right? So over here, the object was just going under elastic strain energy. In this figure too, the object is going under elastic strain energy and also it is going under the gravitational forces. For this case, the change like gravitational potential energy, we have to use this extension as a change in height, the weight of the object as that mg, weight of this electromagnet as mass and gravitational force, right? So now if I go back to this diagram, we have to break down this entire graph into three sections. Okay, so I'll just draw the three sections very quickly. Obviously we have to draw the edge, right, to make it a complete triangle. Sorry. Then again, over here it says that this was the total weight of the electromagnet and the object, right? So we will draw a line over here and a line like this. Okay, so we are going to consider that this is the point that is going to be the weight of your electromagnet. Now let me explain why that we are assuming that this is the weight of your electromagnet EM. That's because if I move up to the original diagram, I should just write this in a very small part. Okay, yeah, that's quite good. Now, in this section, what I was actually trying to indicate is that I'll just remove the forces that in figure 2 only weight of the electromagnet is working in the downward direction, and figure 1 both the weight of the electromagnet and your steel object was acting in the downward direction, right? So I'll just remove these. I'll just write the levels over here. These were the levels of the extension. These were the levels of the wire. As you can see in figure 1, right? This will have the maximum extension because you had a larger force acting on it. But as soon as the electricity supply is cut off, this object will fall off. And when this object falls off, the steel cable kind of recoils in the backward direction. So when this steel cable recoils in the backward direction, this is the delta, or this is the actually delta extension or change in extension that actually occurs, right? That's what we can use in order to find out the gravitational potential energy. Now there the student was indicating that during this time, all the elastic potential energy will be converted to this gravitational potential energy in order to make this electromagnet move in the upper direction. So that's why in this part, in this section of the graph, when this was the position where both electromagnet and object was connected to the steel cable, as soon as the electricity supply cuts off, this one falls off to this part because now the object is no longer connected. So the object has removed, but they will now recoil, right? That's why the force decreases and also the extension also decreases. As you can see, when the this line recoils, the extension also becomes at a lower level. Now, this change in extension was the actual length that we're using. So what exactly happened? This amount of change in force also actually represents your value for elastic strain energy, right? Elastic strain energy that was actually used in order for that steel cable to recoil. That's what the student was indicating, that that amount of elastic strain energy will be equal to the gravitational forces. Now remember, for elastic strain energy, EL, the equation is half force extension, right? Now over here extension is going to be this much. This is the extension, which is clearly fine. But for force over here, which force are you going to use? The force that you're supposed to use is that this force, which is basically the combination of your electromagnet and object, and also this force, which is basically the only weight of your electromagnet, right? So if I just break this down, it becomes half. It is going to have two of the electromagnet and only one of the object, right? So you can just write weight of electromagnet and weight of object, and then delta x, which is basically, if I highlight this section of the graph, like this entire small triangle and this rectangle, both this section are actually representing your elastic strain energy. Now we certainly cannot calculate it because you don't have the specific magnitude of the force and delta x, but again, if you have to focus on that elastic, like gravitational forces energy, gravitational potential energy, for gravitational potential energy we are obviously going to use that this weight of the electromagnet, because after that like steel object was removed, because of this decrease in downward forces, the steel cable will recoil. So only the electromagnet's weight is responsible for that, and then only extension is going to be there. So for the gravitational potential energy, we're going to use the equation mgh, where mg is basically the weight of the electromagnet, not the object. So you just have weight of the electromagnet multiplied with delta x. And if you have to label the graph again, at which portion of the graph it is indicating, this rectangular portion of the graph only, that is indicating the gravitational potential energy. Now you can easily see that the gray area contains of a small triangle than the rectangle, whereas the gravitational potential energy only contains the rectangle. So you can certainly say that elastic strain energy is certainly greater than your gravitational potential energy. So obviously they are not equal, right? So the student statement is certainly wrong. So we'll just explain this over here. So we'll start with that area under the indicated parts on the graph. We'll just write it like this. Um, this one and this one, okay? They represents elastic strain energy. So we'll write that area under the indicated represents elastic strain energy, and which can be calculated using the equation that I've stated. So elastic strain energy, which is equal to, now you have to explain that F again over here, that for elastic strain energy, both the weight of the electromagnet plus the steel object and the weight of the electromagnet acts, right? So you can write that for F, and electromagnet acts, but for GPE, only the weight of your electromagnet is going to work. We can just write weight of electromagnet, okay? Electromagnet will work. Lastly, we'll say that the area under the sections of the graph that for elastic strain energy is greater than gravitational potential energy. Therefore, student is wrong. Is wrong. Okay. So yeah, with this, your question number 16 ends. We'll move on to question 17. It says that scientists use weather balloon to carry their experiment into the upper atmosphere to monitor weather conditions. The photograph shows a weather balloon and upthrust acts on the balloon. The balloon is released from and accelerates upward. What is meant by upthrust? Obviously the definition, an upward force caused by the displacement of the fluid by an object, right? So we can write that and sorry, caused by the displacement of the fluid by an object. Okay. Now they have also given that when the balloon is released, the initial upward acceleration is this much. Show that the weight of the balloon and equipment is about 13 Newton. Volume of the balloon and equipment is this much, and density of the air around the balloon is almost 1.23. Now over here, since we are supposed to find out the weight, um, if it is accelerating, then wait, we can find out the upthrust first, right? Because you have like volume, density, and obviously g is provided to you, right? Rho vg is basically upthrust. So using that rho vg, we can find out the mass of the object again, right? Because you have this delta force, like sorry, um, yeah, you have this upward like up thrust as a resultant force, right? Which is basically up thrust minus the weight of the object, right? And then again obviously your value for your resultant force can be calculated using the mass into acceleration. Acceleration is also provided. So let's just start first with the calculation for your upthrust. So upthrust is rho vg, that is 1.36 with 1.23 multiplied with 9.81. So you approximately get 19.67 Newton. And then again, after calculating upthrust, you get what is it? Weight is equals to upthrust, right? No, sorry. Now you can get, like, since the object was accelerating, that means upthrust was greater than weight, right? This is how the diagram was working. This is weight and this is upthrust. This is upthrust, this is weight. So we can write that resultant force is actually mass into acceleration, and that is again upthrust minus weight. So I'll just not waste any space because we do not have much. So upthrust was your 19.67 minus weight is your mass into acceleration, right? So we can just write mg is equals to m. Okay, g is also known to you, which is 9.81, and again a is also known to you, which is 4.8. So what you can do, you can just take every mass together, which is 9.81 m plus 4.8 m is equals to 19.67. 9.81 plus 4.8, you just add those together, that is like 9, 10, 11, 12, 13. Okay, I'll just take m the subject, and that will be basically 19.67 over the summation of these two, 9.81 plus 4.8. And if you calculate it, you get 1.346 kg. Now again, you have to multiply 9.81 with this, right, to find out the value of your weight, because they were concerned about the weight, right? That is 1.346 multiplied with 9.81. You get 13.2 Newton, the which is quite close to your given data. So yeah, our maths is correct. We'll move on to part B. This is part B1 and this is part B. Okay, so for part B2, it says the graph shows how the density of the air decreases with height above the ground. This is the graph with height and density, and it says the scientists want to make measurements at a height of 25 kilometer where the balloon would stop rising. The balloon will expand as it rises and will burst if the volume exceeds 50 centimeter cube. Deduce whether the weather balloon could support the equipment at a height of 25 kilometer without bursting. Okay, now at 25 kilometer, if I go there, this is your 25 kilometer. At this, approximately the height is like what? This is like 0 0.1. This is going to be like, the density is going to be like 0.05, right? Yeah, it's going to be 0.05 because you just divide 0.1 over 5 and you get every line to be like 0.02. This is 0.02, 0.04, 0.06, 0.08, and this is 0.1, which makes this as 0.05, right? So we can now understand from this part, this is 0.05, the density is 0.05. We already got that upthrust, which was in this part, that was like what, 19.67, right? But we're not going to use that because over here it says that the scientists want to make measurements at a height of this much where the balloon would stop rising. By stop rising, it means that at that height, all the forces were kind of balanced, right? That's why the balloon will not move, and that means that weight would then be equal to the upthrust. So upthrust was no longer 19 point something, it will now be equal to your weight that we calculated in part B1, that was 13.2. So now you can write that upthrust is equal to weight. Then you can write upthrust was basically rho vg, right? Rho is that you got 0.05 from your graph at 25 kilometers. V is unknown, that is the one thing that you are supposed to calculate, right? Rho v, g is 9.81 and the weight was 13.2. So for v, it's going to be 13.2 over 0.05 multiplied with 9.81. If you calculate this, you approximately get 26.9 meter cube. Now, if your balloon to burst, your volume must exceed, like your volume must be greater than 50 centimeter cube or 50 meter cube. The volume that you got at 25 kilometers above the ground was only 27, like almost 27, right? Which is certainly half of that volume. So your balloon will not burst, right? So you can just write that since 26.9 meter cube is less than 50 meter cube, so balloon won't burst, right? So this is it, the final answer for your question 17. B2, right? Yeah, this was B2. Okay. Then we'll again move on to B 17C. It says the weather balloon made of a strong material will rise and eventually stop expanding. It will continue to rise until it reaches a maximum height. Explain how and why the velocity of the weather balloon changes from release until it reaches to maximum height. Where at the maximum height, it will continue to rise until it reaches a maximum height. That means the overall motion of the object of the balloon uh, stops at the maximum height, right? And ignore the effects of viscous drag force. Okay, so you're supposed to consider it like this, that when the balloon is released, initially the upthrust is very large compared to the weight, right? So obviously this causes a resultant force in the upward direction, and according to your like Newton's second law, right, the object will accelerate in the upward direction. But then again, as object accelerates, its velocity increases, which also increases the air resistance. So the air resistance will continue to increase until or unless your it kind of becomes equal to your weight, right? So again, your whenever that air resistance becomes equal to your weight, all the forces are balanced. And another thing from this graph over here, as you have to use data from your graph, we could see that as the balloon rises up in the upward direction, upthrust also decreases, right? As you could see that in part B1, your upthrust was 19.67, but for B2, when your balloon was like 25 meters above the ground, the upthrust was now equal to your weight, which is 13.2. So obviously with increase in height, your upthrust was also decreasing. So in this case, upthrust also decreases, and again, it kind of reaches to a state where the upthrust is, it says that it will continue to rise until it reaches a maximum height, right? Okay, so at as your balloon continues to rise in the upward direction, obviously your weight doesn't change, but your upthrust kind of decreases, and at some point, even if the forces are balanced, right, the object would still be moving with like constant velocity. But over here it says that it continue to rise until it reaches a maximum height where it eventually comes to rest. That means like overall the forces have to become zero, right? Like it's not like that nothing is working on it, but the overall velocity has to zero. Like if it is a case that where the upthrust is equal to your weight, in that case also the object will be moving with terminal velocity, but over here the object cannot move at all. So what would happen is that the upthrust will continue to decrease, and it will decrease far more, where it would become less than the weight, right? It is no longer equal to the weight. Now at this position it is less than the weight. So when upthrust is less than the weight, there's a downward force in the downward direction, like resultant force in the downward direction. Because of the downward resultant force, object will decelerate, and eventually its velocity will now continue to decrease, and it will stop at one point where the velocity cannot decrease anymore because it has reached zero. And that is the case where this object reaches its maximum height and eventually comes to rest, right? So I hope my explanation was clear. So I'll just write down the answer for you. So this is the final answer, where we have written about that initially that balloon is released, upthrust is greater than weight. So resultant force is in the upward direction, which causes the balloon to accelerate, and eventually its velocity increases. But again, as from the information from this question, as height increases, the density would drop, and which also causes the upthrust to decrease. So the upthrust will continue to decrease until it becomes less than the weight, where the object will start decelerating because now it has a downward force, like a resultant force in the downward direction. So because of the deceleration, obviously its velocity will again continue to decrease until it becomes equals to zero. And this is the position where the object or the balloon will eventually reach its maximum height and comes to rest. So I hope question 17C was clear. We'll move on to question 18. Now it says that a student carried out an experiment using a data logger to record the motion of a ball bearing as it fell through a liquid. State the condition under Stokes' law applies to a object moving through a liquid. Obviously, it has to be like a very small radius and spherical, right? And also fall through a fluid that is in laminar flow. So we can just write small spherical object at low speed, moving at low speed. So then again, we'll move on to question B. It says the graph obtained by the student is shown below. We need to explain the shape of the graph. So what is actually, it indicates that if I draw tangent over here, you can clearly see that for the first two lines, which is basically if this is 0.2, this is going to be like for the first 0.04 seconds, your object doesn't have any velocity because the gradient is entirely zero. This is a displacement time graph. Gradient gives you information about its velocity. So during the first 0.04 seconds, object does not have any velocity. Then again, if I draw a straight line, I'll make it quite a fuse over here. I'll try to make it a tangent so that I can understand that which portion of the graph are actually a straight line. Okay, so I can clearly see that over here, this section of your graph is not a straight line. That means during this sections, we can clearly see from 0.04 to almost 0 0.4 seconds, right? During these sections, your object was maybe accelerating. That causes its velocity to change. But after 0 0.4 second, the object goes to their constant velocity where maybe all the forces are balanced because of the acceleration where the velocity was increasing. At this point, the drag was also equal to its weight, right? That's why all the forces got balanced and the object reached terminal velocity, and from this point onwards the object fell to the ground with terminal velocity, right? So again, you can use manipulative data over here or not also include that, because in physics manipulative data are not that much required until or unless they have asked to use information from the graphs, right? So just write that initially, or I think I'll just include the manipulative data. It will just make me make my answer look more organized. So I'll just use it in the first or during first 0.04 seconds. Velocity is 0 as gradient is 0. Object does not object yeah, we can say that object does not have any velocity as gradient is 0. From 0.04 seconds to 0.4 seconds, we can say that the gradient changes, so velocity increases, object might be accelerating, increases, but drag also increases until it becomes equals to the weight. Right, so as I was saying that until it becomes equals to the weight, where all the forces are now balanced, so object will obviously certainly move with terminal velocity, right? That's why from 0.4 to like 1.15, right? We can see it. This object will now move with a constant gradient. So also it increases until it becomes equal to the weight. So object reaches terminal velocity. So with this, your question, I think this is 18 part B1, okay? Yeah, 18 part B1 ends. We'll move on to 18 part B2. So for 18 part B2, it says that the ball bearing had a diameter of 1.6 millimeter. The difference between the upthrust on the ball bearing and the weight of the ball bearing is this much. This is basically the difference between the ball bearing, like upthrust minus weight or something. And we need to calculate the viscosity of the liquid. Assume that Stokes law applies over here. So if Stokes law is applying over here, that means we still have the weight, right? The difference between this much and this is no, this is just the weight. Okay, we have the diameter. From this we can find out the radius, right? And then again from the gradient, if I go there from the graph, since we're talking about Stokes law, so obviously we have to focus on the constant gradient part, right? So I'll just use easy magnet or like easy coordinates to work with. That is, I can find this one to be one easy coordinate because it's quite at the very point, and then again this one, or maybe this one. It's quite easy to work with. Okay, so over here you get 0.5 obviously, and the y coordinate over here is going to be like, this is 10 and 20, right? So you have like 1 2 3 4. Okay, so over here you have like what 20, like 10 difference over 20 lines, right? So every line over here is going to represent 0.5. So you have a point over here which is basically going to be 13.5, I think, right? Yeah, this is 12, 11, 10.5, 11, 11.5, 12, 12.5, 13, this is 13.5, and that was your data, right? So we can write this is like 0.5 with 13.5, and then again over here if you calculate, this is 0.8, and this is 7.5, so 0.8 and 7.5. So again, if I have to find out the delta v or dy by dx, that will be like change in y over change in x. So from gradient you can find out the terminal velocity value. So I'll just write v is equals to, I'll use this working in the lower portions, but as I have data over here, so just calculate it over here. So you get 7.5, 13.5 minus 7.5 over 0.5 minus, 13.5 minus this. Yeah, you're supposed to get a negative value, but because this was in like downward direction, obviously you're just going to use the positive coordinate. So you finally get approximately like 20.9, but this is again for centimeters, so we have to divide it by further 100 to get like 0.21 meters per second, right? Now this was your value for your velocity. So again, if I use it in the given space over there, using a value for your velocity and your radius is going to be like 1.6. As it is in millimeter, you have to obviously convert it into meter. That is going to be 10 to the power of minus 3 over 2. You get almost 8 into 10 to the power of minus 4 meters, right? This is your radius and velocity. We can just use the equation of um, f is equals to 6 pi r eta, where we have to make eta the entire subject of this equation. So it's going to be force over 6 pi rv. Force over here was 1.45 multiplied with 10 to the power of negative 4 divided by 6 pi r is 8 into 10 to the power of negative 4, where v is again 0.21. So if you calculate all this together, you're supposed to get a value of approximately 0.05 pascals per second, or you can just write 0.046 pascal second, right? So this is the value of your viscosity, 0.046. 46. Okay, now for the last part over here, it says that the student heated the liquid and repeated the experiment. Always remember, whenever you're heating a liquid and that question is related to your Stokes law, that means at high temperature viscosity will be low, right? Nothing else to do with Newton's laws of motion or some other thing. It's entirely related to the concepts of that at high temperature your viscosity of the liquid will be low. If viscosity is low, in that case drag, sorry, not drag, then if viscosity is low, in that case like the object will have like a less resistance, and higher velocities can be reached, right? Like higher terminal velocities can be reached. So if we continue the question, the ball bearing took less time, as we have stated that if heat, higher velocity can be reached. Higher velocity means that it now can travel a longer distance within a short time. That's why it says that took less time to fall a given distance in the liquid when the liquid was at a higher temperature. We need to explain this, and we need to assume that the density of the liquid is constant. Okay, so we'll write the answer very quickly, that at higher temperature, the viscosity will be less. So according to V is equals to F over 6 pi r eta, we can now write, I'll just write write the eta separately over here, because as viscosity decreases, velocity is supposed to increase, considering the fact that force and radius are same, right? So we're just going to write that R and drag force, or F, remains same. Therefore, V, like the ball, must now travel with a greater terminal velocity. V term, right? So with this, our Physics Unit 1 October 2023 ends. I hope it was clear enough for everyone.